Hello everyone, I'm Oliver Lloyd Kwaku, a member of Group 24, and I'll be taking you through how to find the transfer function of a translational mechanical system. So in the translational mechanical system shown in the diagram, it's a system that consists of two masses connected by a damper and a spring, and an external force F of t is applied to mass 1, and we are interested in determining how mass 2 responds to that force. Our goal is to model the system mathematically using Newton's second law, transform the equation into the Laplace domain or the Laplace transforms, and finally derive the transfer function. The transfer function will allow us to understand how the input force affects the output displacement in terms of system dynamics. It is a powerful tool in control systems because it helps us to analyze stability, system behavior, and response characteristics. My members will now take you through how to describe the physical components of the system and how we derive the final transfer function.
Hello, please, I'm Abdulminifrad Chalpan, a member of Group 24, and I'm here to talk about the system description. This system contains two masses, M1 and M2, each of them equal to 1 kilogram. There is a spring connecting the two masses with stiffness K is equal to 1 Newton per meter. There are 4 dampers, each with damping coefficients 1 Newton second per meter. The input to the system is the external force F of t applied to mass 1, and the output is the displacement of mass 2 denoted as x2 of t. We define x1 of t as the displacement of mass m1, x2 of t as the displacement of mass m2. To determine the transfer function, we must write the equations of motion for both masses using Newton's second law.
Hello everyone, I'm Mame Akosia Sewa Abusomtwe. Then today I'll be helping to derive the equation of motion for m1. To derive the equation for mass 1, we apply Newton's second law, which says the sum of forces equals mass times acceleration. Since m1 is 1 kg, acceleration is simply the second derivative of displacement, that is x1 bracket t. Now we identify the forces acting on mass 1. First, the external forces Ft. Second is the damping forces, which are proportional to velocity, so they involve x1 bracket t. Third is the spring force between the two masses, which depends on the relative displacement, meaning it involves x1 minus x2. When we sum all these forces and arrange the differential equation, we get terms involving x1 and x2. Then we take the Laplace transform, assuming zero initial conditions. Acceleration becomes x2 x1s. Velocity becomes x1s, and displacement becomes x1s. So after simplifying, we get the x squared plus 3x plus 1 x1s minus s plus 1 x2s, which is equal to the force. The fact that both x1s and x2 appear shows that the two masses are coupled through the spring and then the dampers. Thank you.
Hi everyone, I'm Amweni Charles MC, and I'll be explaining how we derive the equation for M2. For mass 2, there is no external force applied. However, it experiences forces due to the spring connecting it to mass 1 and the damping elements attached to it. Applying Newton's second law and transforming to the Laplace domain gives x squared plus 2x plus 1 multiplying x2 of x minus x plus 1 multiplying x1 of x equal to 0. We observe that x squared plus 2x plus 1 can be factored as x plus 1 all squared, and this factorization will simplify our calculation significantly in the next step.
Okay, so we have to express x1 in terms of x2. From the equation for mass 2, s plus 1 multiplying x1 of s is equal to s plus 1 squared multiplying s2 of s. We divide both sides by s plus 1, assuming s is not equal to -1. This gives x1 of s is equal to s plus 1 multiplying s2 of s. So this result is important because it allows us to eliminate x1 of s from our system of equations instead of solving two simultaneous equations directly. We reduce the system to a single equation in terms of x2 of s.
Hi, my name is Yvonne Deizanga, and I'm taking off from what the last person just presented on. So then we are continuing. So now we substitute x, that is x plus 1, x is into the first equation, and it would become that's fs is equal to x squared plus 3s. Like this equation, fx plus x squared plus 3s plus 1, then s plus 1 multiplying xs minus s plus 1 multiplying x2 of s. Then we factor out x plus 1 x squared, x plus 1 x subscript. Yes, yeah. So then that's that about this part. So then we substitute the x1 into the first equation, and after that we factor out the x plus 1 x squared s.
Hello, my name is Gideon. I'll be explaining simplifying and factoring. We now simplify the expression inside the bracket, which is s squared plus 3s plus 1 minus 1, which becomes s squared plus 3x. Next, we factor s squared plus 3s, which is equal to x into bracket x bracket 3. So the equation becomes x squared from here, s squared of x plus x, which is into bracket s plus 1 in bracket s plus 3, which is equal to f of x. This form clearly shows the structure of the system dynamics.
My name is Fahad Aruna, and I'll be taking you guys through the transfer function. So under the transfer function, we divide both sides by the denominator. That is, gen of s is equal to x2 of s divided by f of x. Therefore, gen of x is equal to 1 over s bracket open, s plus 1 bracket close, bracket open, s plus 3 bracket close. Now to the expansion, we have gen of s is equal to 1 over s power 3 plus 4 over s squared plus 3 over s. This is the required transfer function of the system. Thank you.
Hi, my name is Musa Mohammed, and I'll be taking you through the system interpretations. So for the system interpretations, we'll interpret the result. The poles of the system are the roots of the denominator. S is equal to 0, s is equal to -1, and s is equal to -3. The pole at the 0 represents the interpreter. This means that a constant force input will produce a continuously increasing displacement. The poles at -1 and -3 are the negative real poles, indicating stability. Since there are no positive poles, the system is stable. However, due to the pole at 0, the system will not settle to a fixed displacement under a constant force. That's it.
So, in conclusion, we've applied Newton's second law to both masses. We've also transformed the equations into the Laplace domain, solved the coupled equations, derived the transfer functions. This process demonstrates how physical and mechanical systems can be systematically analyzed using mathematical